Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
For the invitation. Thanks for running this workshop. I'm looking forward to having 2 interesting days. It's an honor to be the first speaker, but it's also an obligation and a risk. You do realize, and I realize certainly, that this is a minority topic. So tapping into unstructured data, text essentially, is not the mainstream of big data. My goal for this hour is to convince you that it deserves way more attention than it has. So why do we work on big data at all? So this reminds me of that question, why do you want to climb the Mount Everest? This was asked to George Mallory, a mountaineer who was one of the first who wanted to climb it. And his plain answer was because it's there. Now, this is a good answer for a mountaineer, but I don't think it's the answer that Microsoft or any university or academic player should have for that question on big data. This is not the way to attract industries big money, for example. And it's not the way to get onto the front page of the London Times, especially in the nonfiction section, as you see here. So the promise of big data is more, and we have to keep this in mind. So we're not just, let's manage huge amounts of data. The largest number wins. So if what is after zettabytes, right? So these kinds of games is not what big data is about. We start with interesting data on energy, health, traffic, etc. And then we do have a big machinery, a big data analytics machinery, and many of us know how to do these things at large scale, or this is also a good piece of the research in this area. But then the main point is, at some point, some human has a deep insight into something and this insight should be actionable. So actually we should change the world. We should make the world a better place. Solve the world's traffic problems, as you see here, or solve the world's health problems. Now, if this is the goal, so it's not about just managing huge amounts of data, it's about gaining insight and improving something in the real world, why don't we ignore mankind's best intellectual assets? So the best intellectual content that mankind has produced is in written form, is in text form. It's in essays, in news articles, it's in books, it's in scholarly publications, maybe even in social media, maybe in Facebook, who knows? But it's not just some number in some database, right? This one number in the database is not a big intellectual contribution. So we should not ignore this. This is my point. So I'm going to continue a little bit longer on interesting data, making that connection with text. And then I have a main technical part on moving from surface names that we spot in text, but perhaps also in wake form, in ambiguous form, in a structured database, and then turning this into a crisp entity. And then the analogous story for relations, and then a short part towards wrapping up. So interesting data. So there's the wide belief that structured data is good and unstructured data is bad. But when you look at this comparison here, so you see a table with locations, but then Northern Territory, what kind of location is it? This is a part of Australia that's larger than Central Europe. So we measure the temperature with 4 digits after the decimal point. So what does it mean if it's a huge area? The time is just a whole month. It's not even saying which month, which year. And is this average temperature averaged over time in one point, averaged over time and space? What exactly does this mean? So this looks cool, but the value for gaining insight is actually not so big. In contrast, you look at this text. It's text, yes, but for a human, it's way more informative than the piece of data that you see on the right-hand side. So the goal should be to do with machines what humans can do already, right? So we need to get that insight from the text as well. Second example is about health. So these are side effects of some medical drug. And it's official information. It's a list, but we can easily cast this into a table. It's structured data. It's a long list. And why is this? Because it may come from a pharmaceutical company. So these guys have to be conservative. They would list each and every possible, potentially conceivable side effect here. Now, which ones do actually occur? This is what gives you insight, not this super conservative super list. And to get that point, that information you have to read. You have to go to the biomedical literature where people did clinical studies, and these studies would say this rarely occurs, this has never been reported, this has often been reported. Or you even go to social media. There's plenty of online discussion forums about health where people report their subjective experience. Of course, it's subjective, it's noisy, it may even be spam, but then you can aggregate over many of these. So my point is that the world is not black or white, good and bad, but it's much more complicated, and both sides have their value, and the combination actually has the best value. Of course, to get that value from text, one crucial piece is to identify the entities of interest. So we have to identify Darwin and infer that it's a place in this area. We have to identify the truck that is being mentioned, the names for the side effects, and so on. So the truth is in the middle here. So connecting structured data with unstructured data, I think, is a direction to pursue. And one of the playgrounds for academics, at least one of the most interesting playgrounds, is the web of linked open data. It's a huge collection of structured knowledge and data sources, which you can connect to text. In total, more than 50 billion subject, predicate, object triples. So there's some knowledge bases here in the middle, but there's all kinds of specialized data assets as well on life sciences, on music, on movies. There's in the upper left corner, here there's a cute little knowledge base about beaches and surf opportunities. There's one about coffee, but only in Russian, and so on. So what do we have in these? So this could be information or knowledge about Amy Winehouse, who lived and died not too far from here, maybe 50 kilometers from here in London. And so you see these subject, predicate, object triples. But how did they get into these knowledge and data sets? Well, they were actually extracted from semi-structured data sources like Wikipedia. So a lot of this comes from info boxes, from category names, from headings, from lists and tables inside Wikipedia. But some of that also comes from doing information extraction from text. And that gives you provenance, where do these facts come from, but also additional information. So additional descriptions of the special circumstances on why and how did she actually perform this song, Cupid, and who was the original composer, and who else has covered it, and so forth. So it's not just Wikipedia, it may be news articles, web pages, and so forth. So this is connecting structured data with text, but because we actually pulled a lot of that structured data from text, and this is the direction where indeed we view text or web pages as primary, web contents, but we can identify now entities here. So in addition to Amy, we have Janis Joplin and Jimi Hendrix, and now we can map these to the web of linked data, to the knowledge bases, to structured databases, and this combines whatever the text says with some additional facts like birth and death dates, and then maybe we can automatically infer that weird or infamous notion of the Forever 27 Club, and that they are all members of that infamous club. There's plenty of structured microdata now embedded in HTML. So these are little RDF-like structured pieces of information embedded in web pages. And there's, of course, tables in web pages. But these are not database tables. They are just HTML tables. So there's no schema. There's no real typing for the columns and so forth. And this is about covering songs, secondhand songs, about Amy Winehouse, but Amy is dead, so the list is not so big and it won't be growing further. So I have a second example. Ennio Morricone, who's an 85-year-old Italian composer, famous for film music scores. And this is a very, very long list. And this is not the only one, or table. This is not the only site that has such things. So here's another one. Now you can start comparing things. And this is interesting because it not only says, well, he was covered by the following artists, but it also says he sampled pieces of compositions from other people. And he blended them into his own compositions. And so this tells you that he was influenced by a bunch of classical composers. Now, this is kind of, you can still think of this as structured data, but now it's definitely non-schematic. So it gets much closer into text form, into unstructured form. And most people would think of it as unstructured data. Moreover, there's a ton of context here. So even if you think of a table in a web page as being structured, but to understand what it says, you often have to look at the context. So there's often a description of the table, some discussion threads, like as shown here, right, for this specific site. So let me cast this into what I call the big data and text challenge. So take all that data, use public data and public text. There might be proprietary databases in the music industry, but then there's probably no single proprietary database that has everything. It's a very dynamic industry. And then find out who covered which other musician and which versions were the most successful ones, or more generally, who influenced whom. So you might think this is peanuts, but you have to realize you might have to analyze all of YouTube, and YouTube is not exactly small data. You might think it's my personal obsession, maybe you're right, but then there's other examples. So in health, I spell one out about side effects of drugs, and I'm sure I can come up with examples in these other areas as well. As a general design pattern, go after the assets, data, and text, identify entities and maybe relationships between entities, then position them in time and space, because this is often where the insight comes from. How does America differ from Europe? How were certain things evolving over time? And then there's the usual group and aggregate machinery. And finally, want to find insightful patterns and predict trends, etc. So now in the technical part, I will focus on this part here, on identifying entities of interest and actually addressing the ambiguity, because what we see in these non-schematic data and in the text is actually just a name. So these names can have many different meanings. So this is now the technical part. Milan, you will guide me with time, right? So because there's some part towards the end which I could also skip. So just to drive my point home, here's another example. This is what linked data knows about Ennio Morricone. The people at Derry in Ireland have some nice tools, so you can search with a name, and they give you all the RDF triples that have facts or knowledge about this entity. And so there's plenty of these subject, predicate, object triples. The subject is always Morricone. This is what I searched for. And now let's zoom into some of them. And this is kind of odd. So you realize that Morricone has an absolute magnitude. He has an apoapsis. He was born in 1928, but he was discovered in 2005. Strange. And he has an epoch and so on. So what happened here is that there's actually two Morricones. They were not kept apart. There's Ennio Morricone, the composer, and then there's an asteroid which passes by Earth once in a century, and that asteroid was named after Morricone. So interesting, even such a highly specific name, Morricone. Right? This is not the Joe Smith of Italy, right? This is a rare name. So, but even that is not unique. So you face ambiguity everywhere. So now I'm going to walk you through like the state of the art in this entity named disambiguation, essentially. And it's part of our work, but also without making everything explicit, there's other people's work worked into this as well. So let's take this example text. Sergio talked to Ennio about Eli's role in the ecstasy scene and so on. And the question is, who is this guy Eli, right? Is this Eli from the Bible, or is this guy Eli Wallach? First thing is, how do we know that we have these options? Well, and also it's not the only name that occurs here. These surface names that we think could denote entities, but we don't know which entities, we call them entity mentions. And mapping them to real entities, saying Eli is, for example, Eli from the Bible, this is the actual disambiguation. So there's first a recognition step, but the recognition, actually it's called entity recognition in the literature, but it's actually recognizing mentions, names. And CRF's conditional random fields is a state-of-the-art techniques for doing this. And this only gives you the names that are marked here on the left side. The mapping to the right side is the actual disambiguation. The combination of both is sometimes called NERD, named entity recognition and disambiguation. So knowledge bases or that web of linked data, and you can also think of product catalogs if you want a business application. So they give you huge numbers of pairs of names and entities that might be denoted. But this is not yet the disambiguation. It just gives you a candidate space. So you see that ELI could also be an acronym, meaning extreme light infrastructure. Ecstasy could mean methyl dioxide methamphetamine. I practiced this 5 hours. So this is the drug, ecstasy, obviously, and so on. So this way we get a space of, or a set of possible candidate entities, and then we can also generate systematically the set of, or the space of possible mappings. And one of these mappings is the correct one. And disambiguation is computing this correct mapping. So there's 3 main ingredients that all the methods use here in various forms and with additional bells and whistles, etc. So I'm simplifying here a little. So the first ingredient is the popularity of a name-entity combination. If we just hear Eli, we probably think Eli Bible. If we just hear ecstasy, we think drugs. So how can we estimate this conditional probability of an entity given a name, and only that name, nothing else, no context given? So the entities that we consider here in our entity repository, product catalog, or knowledge base, they often have textual descriptions. In the knowledge bases in the web of linked data, these are typical Wikipedia articles because there's a one-to-one correspondence between the entities and the Wikipedia articles. This is also, for example, the case with the Google Knowledge Graph, and I think Microsoft must have a similar project. I don't know the name. So, and Wikipedia, or whatever asset you have here in the background, often comes with some cross-references. So in Wikipedia, these are hyperlinks, and hyperlinks are name-entity pairs. They have an anchor text, which is usually a short name, sometimes an acronym, and then they point to an article, which is an entity. So this gives you a handle for estimating these conditional probabilities. Of course, popularity alone, this is kind of a prior. Right? You cannot work with this alone because it would always prefer prominent entities and never go for the not so prominent ones. So it's only in combination with the other ingredients that this helps. And the main ingredient that people usually consider is context similarity. So we have here a dimension Eli, and we can construct a textual window around it and cast this into a bag of words model, or maybe a statistical language model over words, phrases, whatever. And we do the same with the textual descriptions that we have for the entities on the right-hand side. So with Eli Bible and with Eli Wallach. And now we have apples here and apples there, and we can compare by different kinds of similarity measures, like cosine similarity, Dice coefficient, Kullback-Leibler divergence, you name them, depending on how exactly we created the models. And obviously the higher similarity is more likely to be the right entity. The third ingredient has to do with the situation that we have a set of mentions at our hands, and it's beneficial to do joint inference for all of them together. You might think you want to process them one at a time by cleverly ordering them. So, for example, you mapped Ennio first, and Ennio is also a rare Italian first name. So once you have Ennio Morricone, a lot of the other things fall into place. But finding that right order is non-obvious, and maybe you start with ecstasy first. If you start with ecstasy, you are bound to move to the truck, and the rest will go wrong as well. So it's much better to do this jointly in one big inference step. And from the semantic perspective, the asset that you can leverage here is the semantic relatedness of entities, or coherence. So these entities don't co-occur randomly, uniformly. Why would a web page mention Eli from the Bible, the drug ecstasy, and the Lord of the Rings trilogy in one together, right? So there's no connection. And that is a consideration that's independent of how you phrase it in the actual wording, right? So it doesn't matter what words you choose and what else you say about them. They're just very unlikely to co-occur. And in these situations, when you have a multivariate data space, the sweet spot is typically go for the pairs. So we can compute a coherence measure for pairs of entities. And if this is a quantitative measure, we can turn these into weighted edges that connect the candidate entities on the right-hand side. And the weights can be derived from different ingredients. So one is a type system, or it could be a category system for a product catalog. But here we use semantic classes for entities in a knowledge base. And we look at overlaps and how close are the different types in the taxonomy. The type taxonomy here is a huge DAG with several 100,000 of nodes. Or if we have Wikipedia in the background, why not use it? It has a rich link structure, so we can look at overlaps in incoming links or outgoing links, or maybe both. Or, and that's actually the most interesting direction because it's the most generalizable, we do another text mining task first. So we mine key phrases that are salient for entities. So this by a mutual information argument salient. And then we can look at overlaps between the key phrases of different entities, of a pair of entities. And even if there's no exact match between the phrases here and the phrases there, there's often partial matches. So if you have the right matching model here, you can still infer that, I don't know, I should point here, Ennio Morricone composition and soundtrack by Ennio Morricone, there's a big connection, obviously, without understanding that Ennio Morricone is a name of a person, etc. So putting everything together gives you a graph construction like this, which is almost bipartite, except that you have these additional edges here. So these are mentions, and these are candidate entities. And now we need to work with this kind of graph, and there's different approaches. One is to view this as from a machine learning perspective, as a probabilistic graph, where the model is kind of a probabilistic generative model, this one here. So given a set of entities, what's the probability of seeing these mentions, these names? And it's a multivariate space. Again, you have to, for tractability, for sparseness, essentially. It's not just computational cost, but also data sparseness that forces you to factorize. So you have to make conditional independence assumptions, and that typically leads to looking only at these pairs of couplings here, and then these are the factors in a probabilistic factor graph. Essentially, all the edges in the graph become factors in a probabilistic factor graph, and then you have the whole machinery, Monte Carlo, Markov chain, sampling, casting this into integer linear programming, relaxing this into LP with randomized rounding, you name it, right? So the literature is full of this. All of this is expensive. And these graphs are not necessarily as small as they are in PowerPoint. So if you have many of these names, have hundreds of candidates, so you quickly, if you have a decent sized text, you quickly have a graph which has 10,000 nodes or several 10,000 nodes on the right-hand side. So an alternative modeling is to think graph algorithmic. So within that big graph, we want to compute a smaller graph, maybe a dense subgraph, where density could be the total edge weight that we pick up from that subgraph, and we have to satisfy constraints, namely that each mention left is mapped to exactly one entity right, otherwise we haven't disambiguated. Or if we allow partial mapping, so some mentions are just, they are too exotic, so we say, well, we don't map them at all, we map them to null, then to the constraint would be map each node left to at most one node right. So, of course, NP hard. Huh? It turns out all these give you decent solutions, but you can do better. The reason is that, especially the last model with a dense subgraph, often tends to produce subgraphs that have multiple clicks, a click here, a click here, a click there, and then very loose, low weight, very weak connections in between. And then from the semantic perspective, when the human later interprets the result, it's broken. So the output is poor. And what we want to do is we want to make the weakest link in these coherent structures as strong as possible. And this is what we could formalize by looking at weighted decrees. So the weighted degree of a node is the total edge weight of its incident edges. So when you look at the 140, it comes from this 10 here, plus 50, plus 50, plus 30. And making the weakest link as strong as possible means maximizing the minimum weighted degree in this subgraph. I'm simplifying here a little because in the subgraph, the weighted degrees are smaller, and I kept the original ones. The final ones are the ones that matter. No free lunch, everything is NP hard here in this space if you want to consider the crosstalk among the entities, right? You can come up with some clever feature engineering that avoids that computational complexity, but then it becomes really ad hoc, black art feature engineering. And it's also not equivalent. It's not the same, right? So you simplify and you lose some of the benefits. This is the method that we use in our tool. The tool is available as open source, and we also have a service who can try it out, including a little demo. There's one technical ingredient which I want to bring out here. I gave you the simplified picture so far, and there's several bells and whistles in various spots, but this is one of them. So I said for the mention entity similarity, do bag of words similarity measures. That's what you think of after a hot shower. But doesn't go so far. So there's a much better way. Because we have these key phrases associated with entities. So if we think of the entity ecstasy of gold, the composition, that's a musical composition, and it has a Wikipedia article. So but also articles in music online forums. So you can mine characteristic key phrases and quantify their salience by pointwise mutual information. And Metallica tribute to Ennio Morricone might be one of the key phrases. Now we look at an input text like this one. The ecstasy piece was covered. Here, this is the mention. And the candidate entity we're thinking of is ecstasy of gold, but it's not spelled out here. So now we try to match the key phrase in this text. But these are phrases now. They're more expressive than single words, but then they're also rarer. So it's bound to have low probability of being matched exactly, so we need a partial matching model, and this is what we have done here. So we try to match as many of the tokens of the phrase in a small window, which we call the cover. So that cover kind of should maximize like the ratio of number of matched words or tokens over the size of the window. And there's a scoring model behind this. The details don't matter here. We can do this for all the key phrases for one candidate entity and aggregate then over these scores. And then we have to do it for all candidate entities for one mention, right, to compute this. This is actually a computation that constructs the graph as part of the graph construction. It's not yet part of finding a dense subgraph. So I hope I convinced you these are computationally difficult and challenging problems. So here's a screenshot demo. I have this running example with some little variations. Don't get irritated by these double brackets here. So we use a Stanford NER tagger for finding mentions, and that is good in precision, but not so good in recall, so we help it a little. This is kind of a de facto standard notation in computational linguistics. So when we get everything right here, even the Dollars trilogy, and also Yo-Yo Ma, the cello player. And the candidate space is big, so trilogies, the knowledge bases know many hundreds of different trilogies. Here's a very tough example, and also a British example, not Italian. Page played Kashmir on a Gibson, and why would Larry Page meet with Mel Gibson for playing chess near the Himalaya? Unlikely. So this is Jimmy Page from the legendary Led Zeppelin group, here from the UK. And he played that song on a Gibson guitar. You can also take as input tables or a set of RDF triples. The model is very general. Of course, then you may want to add additional considerations, right? I'm not saying this is the best model for that, but it would work. So here's this made-up table, Steve and Mac, Dennis and C, Richard and Knu, and it does a decent job of mapping these to named entities. So there's systematic studies, including a recent dub paper by Paolo Ferracina on the nerd topic, so which includes the recognition, the mention recognition, which changes the picture a little bit. So I'll skip this now in the interest of time, give you some pointers here to other people's work with focus on online demos that you can try out. So what's going on here? What is future work items? Of course, there's always room for improving the efficiency, especially when you're thinking you want to have this and do this in real time. So consider someone browsing a long text. maybe a book, or maybe scholarly publications, journal articles. And as you browse, you should immediately see which entities show up where, and at least the most prominent ones. So here efficiency matters. High throughput, NERD, if you want to process a big batch, say 1 day's postings in all the social media of the world, or maybe just the YouTube postings, you could even think of this as a stream input. There's issues with long tail and newly emerging entities, which I'll come to in a minute. Short text and very long text, like tweets and books, are difficult for very different reasons, but then there's also inherently difficult texts, like fictions. You can apply it to tables and lists, so structured, non-schematic structured data on the web. And of course, it's a special case of a more general word sense disambiguation problem, which in full generality is maybe interesting for computer linguists, but not for real practice. But there's some other classes, especially verb phrases, often denote relations. And disambiguating these into relations that you can actually then look up in a database is of interest. And I'll have a little part on this in a few minutes. So time-wise, I'm doing fine, right? So long tail entities. Here I have a different example about Nick Cave, an Australian singer. And so he has a song, Hallelujah, and there's a famous Leonard Cohen song, which has been covered 1 million times. But this Cave song is a different one, just happens to be the same name. And why not? This is not a patented name, and there's even Bach choruses with that name and so on, right? So there's actually so many different Hallelujah songs or compositions. So that Hallelujah is not in Wikipedia. It is in Last.fm, which is like a community platform on music, a pretty big one. And so if we relied for coherence only on Wikipedia links, we would get a very sparse graph, and we would be misled and do weird mappings. So instead, what we do here is we use a key phrase model also for coherence. I introduced it for the contextual similarity between a mention left and an entity right, but it's also good for looking at entity pairs. And it's more general than what we did with Wikipedia, because key phrases can be mined from whatever we have. So Last.fm, once we know here's a page about this entity, a ton of user comments about it, we can do key phrase mining. And so we have done this, and then we use the key phrase set overlap measures, essentially, in order to compute a coherence graph like this one. And this is a much more expressive coherence graph and gives us much better disambiguation mappings. There's some specifics here about how these overlaps measures are computed. It's a two-stage process because we compare two key phrases from the two entities. And then they might have a partial overlap. So here we use a weighted Jacquard coefficient. And then we need to look at the sets of all key phrases on both sides. And there's efficiency issues in the implementation, so hash sketches play a role here to speed things up. Now, some entities are not in whatever entity repository we have at all. So how do we know? And when should we say, well, we don't map it at all, because any mapping we do is bound to be wrong and might actually affect then, in the joint inference, the mappings of the other mentions. So we can do actual damage to the other mentions. Instead, we should say, let's map them to null. So one approach along these lines is to say, well, we introduce pseudo-entities, which say for these mentions waters, edge, and mermaids, any other entity with that name. And that's like a mention-specific form of null in our model. And for these, we can mine key phrases by looking at the occurrences of that name all over the web or all over a huge corpus. Could be a digital library, whatever. And then from that, that's like the universal key phrases for that name, not for an entity. But then we have the other candidate entities, and they have key phrases, so we can now subtract models. Either if they are sets, subtract sets. If they were statistical language models, we have to work a little bit with this, but we can still do this. And then these pseudo-entities, the null mappings, become part of the regular model. So we don't need to invent anything special, and I think it's a principled model for dealing with this issue. Now, if they are not mapped, so then they stay mentions. So we pick them up, we would say, here's a piece of text, we found the following 20 entities that occur here, 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 and then in addition there's 50 names which we can't figure out. But you can actually handle them, you can cluster them, you can group them, and in computational linguistics this is known as cross-document coreference resolution. Coref resolution is within one text, where mostly you would say here's a pronoun and this actually denotes or refers to the following noun phrase further up in the text. But you can generalize this across documents. And so in this example here, we could map these two mentions to a known entity, these three, but then maybe these here, there's no fitting entity in the repository on the right-hand side, so we don't map it at all, but we can cluster them together, group them into an equivalence class, and do this across documents, likewise for this guy and for another one. So there's plenty of work on this cross-document coreference resolution. It's a textual counterpart to entity resolution. You merge 10 customer databases and you form equivalence classes. It's a little more general because here you have multiple, you have kind of duplicates per data asset, right? So each document can mention the same entities many times. In a customer database, in each database, a customer should be only once. But you never know. I mean, world is messy sometimes. But the combination would be looking at NERD and this CCR problem together because there's potential synergies. It has not been done yet. So why is this all about big data? There's plenty of big data ingredients here. Web scale, key phrase, and statistical mining. If you prefer these machine learning probabilistic graph models, so then there's maximum a posterior inference, which is a tough problem. Or you are more into graph algorithms, then subgraphs is notoriously hard. And we even have variations of this. The underlying infrastructure data, web of linked data, knowledge bases, they are big by themselves. And just constructing the graph is not a piece of cake, right? You have to do lots of lookups to these underlying knowledge bases. Unless you speed them up and you cache this, you cache that, you're ending up with minutes of response time rather than a few seconds. And there's applications conceivable to large scale input batches, like find all the entities in a week full of social media postings, maybe with a special focus, or look at 1 month of scholarly publications on some diseases, so that a life scientist can kind of get a power briefing on what's new in my area and that would potentially interest me. And here thinking in terms of entities and not just, here's 10,000 abstracts and new abstracts in PubMed. Nobody's going to look at these, right? Or you are a journalist or a political or business media analyst, and you want to track a set of people over in a news archive over several decades. So I have 15 more minutes. Is this correct? Or yeah, okay. So much for mapping names into entities. And now we're going to look at the counterpart for the relationship. So my model of the world is an entity relationship data model. So why is this important? Well, if we want to tackle that task, who covered whom in music? So we need to learn to read these sentences. And the wording for covering another song or another artist is very different. It's widely diverse. So there's cover songs by, interpretation of, singing of, voice in her version of, performed, sang, and so on, right? So for the purpose of this conceived big data analytics, we have to find equivalence classes. We have to understand that so many of these phrases are equivalent for that purpose and that they actually denote paraphrases of that postulated relation singer cover song. And likewise, for who created which or composed which song, because what we're actually after is a join between singer performing a song and song created by another musician, right? So in the end, we want to know who borrowed material intellectual property from whom. Okay, so one recent piece of work that we did, again, we're not the only ones. In the slides, I didn't want to put references on every slide. I put references to our own papers, of course, but not to other people's work. But I and a co-worker of mine, Fabian Sochanek, we have a tutorial in the upcoming SIGMOD conference, which has a 5-page thing in the proceedings and has 150 references. It's not the same, directly the same topic as this talk, but it overlaps. So you can get references there. So the contribution we've come up with here is a concept of syntactic lexical ontological patterns. So syntactic lexical is standard. It's essentially about using like word patterns, maybe with some syntactic generalizations, like in particular using so-called part-of-speech tags, which are word categories. So you say, well, there's this pattern, but there's one word in the middle that always varies, but it's always an adjective. So then we actually say, well, there's a pattern, a syntactic or lexical pattern, this word, any adjective, and this word, right? So this is standard, but ontological is the new thing here. Here we use semantic types like singer, musician, etc., or bass player, or left-handed electric guitar player like Jimi Hendrix. These become now part of the patterns. And there's a notion of because in the end we want to also have a quantitative measure of strength of a pattern. So there's some statistics involved, and we have a notion of a support set here. Where we say, well, we have co-occurrences of a pattern with a pair of entities, and this pair of entities fits with a pair of types that we say form a good pattern. Here's examples. Singer's adjective voice, any wildcard in song. So the type signature is singer by song. You see instantiations of the pattern, and you see a support set here. We did this at large scale using different ingredients like the full text of Wikipedia, a big web crawl, etc. And here's some examples, and you see that the type signature goes a long way. It helps a lot in interpreting the patterns because there's one pattern covered that is actually at the surface level identical for two different relations, and we can keep them apart by having type signatures. So a singer covering a song has nothing to do with a book covering an event. We have mined synonym sets. Including the generalizations with part-of-speech word categories, and even subsumption relations. So it's available online. I'll skip this. There's some examples. Why is this, again, big data? I'm not saying this is the end of the story. We're not claiming victory, because when you look carefully, you find lots of noise still in the output, right? So there's we haven't conquered or succeeded completely in dealing with the precision recall trade-off in this space. So there's more work to be done. Well, at the heart of this is frequent sequence mining. And this is how we implemented it, actually, where we utilize this generalization hierarchy. So any word can be generalized along the word category, shallow generalization hierarchy, and the types actually have a pretty deep generalization hierarchy. And so as we see that certain combinations don't have enough support, we can generalize. It's just like in association rule mining. If we don't have enough support for, let's say, peanuts were bought together with Coke, then we generalize into snacks with soft drinks, right? So this is what's happening here. A lot of our machinery is MapReduce parallelized. Not everything, but the core pieces. And I think it's a decent piece of work, but especially if we want more data at larger scale, some of these will break again, right? So then we need new ideas of algorithmic nature. Ongoing research here is indeed countering the sparseness, especially the subsumption hierarchy. I'm not so happy with that. So it's very sparse. That has to do with the sparseness in the input data. So we would need larger web crawls of higher quality. The one we use is this Clue web crawl from 2009 that CMU provides. 500 million web pages, but still there's a lot of crap in it. So it's much smaller. It doesn't give you the mileage that you would love to have. And therefore, having to cope with even larger scale input is a challenge. Crowdsourcing might play a role here. And of course, brute force, it's trivial, but brute force is prohibitively expensive, so you need some smartness. And there's applications of utilizing these type signatures for patterns, in particular in using these typed patterns when they co-occur with mentions that might be newly emerging entities. So we don't have them in any of our entity repositories yet. They help us in at least inferring a semantic type. And that helps in turn in the life cycle of maintaining all these entities, because once in a while you would tell some expert, so we found the following name 50 times, and we think it's always a new musician. Maybe it should be entered into the entity repository, right? The pattern synsets also play a role in translating natural language questions into structured queries. So we would ideally like to have interaction, especially if the world moves towards speech-based interfaces with our smartphones and so on. Then it's much more natural to use natural language. So nobody wants to talk to a smartphone, select star from so-and-so, right? And even keyword search is artificial in spoken form. So we need to map them to the available relations and attributes in the underlying data. And this is one of the assets here. I'll skip this part. And so I have a short wrap-up on the bigger picture and then the true wrap-up, the summary. So I started with this challenge, right? So who covered whom? I think it is a challenge. I think working on this as an example would be very fertile from a research perspective, even without solving that actual problem. I'm not so keen on solving that specific problem. And as I mentioned earlier, you find similar or kind of isomorphic analytic tasks in health, politics, business. And I want to remember you about this general design pattern. And the talk was only about the first stage here. The other stages are non-trivial as well, right? So there's plenty of challenges in the other stages. In grouping and aggregating, although we've done it in SQL for 30 years, but now you apply it at a larger scale with different kinds of input data. So once text is involved, there's also a lot of grouping and aggregation over variable length n-grams, for example, and this is not so easy. So I have two more application examples. One is from the past, and the next one is from the future. So this is from the past. This is computing big disease networks, which created some splash in the life science literature 6 or 7 years ago. So they looked at all the PubMed articles, or maybe the full articles, Medline, which is like the largest digital library on life sciences. And then they created these nice-looking graphs of how human diseases relate to each other at the phenotype level, what you observe in patients, and at the genetic level, the genotype level. And but these graphs, they look so nice and impressive, but they cover up one shortcoming. I believe this was done just by looking up name co-occurrences. So the notion of relatedness is a very soft one. They are related, but how exactly? There's no refined notion of which relationship. And also the disease names were just simple names. So it did not do any entity disambiguation here. And this is what you would actually need when you realize, for example, diabetes is a family of diseases. There's certain variants, and there's maybe 50 or 100 different names. And so many of them are synonyms, but so many of them actually denote different variants that you shouldn't confuse with each other. I don't think they have solved this. So this is still a challenge. And this is a future application. It's a killer application, sadly, in the literal sense. So consider doing really big picture opinion mining on the political landscape on gun control. Some controversial issue, and here I pick gun control, because it's a typical US topic, but maybe it was an incident in London, again, some killing, so who knows. And this is really a challenge, because you need to identify the entities that play a role, and they're not just Obama and some other guy, right? So really at larger scale, going into the long tail of interesting entities, all kinds of organizations that are behind them, then refined by gender, geo-region, cultural background. So there are lots of things to consider. Do analytics over time, in particular, because you want to see how opinions change before, after certain incidents. And the incidents are not directly given to you. So you may just start with all the news articles in the world from the last 10 years and all the social media postings. And that's a big challenge. And there's tons of technical challenge you can derive from this. So summary. So I believe entities and relations are the key to connect structured data with unstructured data. You spot a name here, and once you know this is the following entity, now you can connect it with structured data that you have about this entity. It's even in the structured data world, because structured data does not mean there's a schema and every entity is precisely nailed down, right? So, but lots of names are still ambiguous even in structured data. So the disambiguation is really a key problem. I believe the state of the art on entity name disambiguation is not bad. It's not just our work, it's a bunch of people. I know the companies like you guys, Microsoft has good work on this, Google has good work. So I know Google uses some of that in their search interfaces and recommendations. Microsoft probably too. I just don't have any direct insight into this. And so entities are crucial for big data analytics on data and text. And as I previously mentioned, I believe we're going to see more speech in the future. And at some point, we want to tap into video. And the part of videos that is where we have some hope, where there's light on the horizon, is the speech track. So then once we have a handle on this, then we can combine with, let's say, some object detection in some of the stills from a video. Take-home message, I connect structured and unstructured data. Entities and relationships are key for this. And if you can solve my personal challenge, who covered whom, I think you can solve lots of other interesting things. Thank you.